Hello everyone, welcome back to CFD College. I'm Ashkan and this is another tutorial about ANSYS Fluent. And this is the second session of the simulation of flow over a flat plate, as you know. If you haven't watched the first video of this specific example, please go ahead and watch that and then come to here to this video. So, if you're new to the channel, please subscribe it. Please give us a thumbs up and share these videos with your friends. That's the best support that you can do for us. So, as you remember, we did simulate the flow over a flat plate in laminar flow, and now we are going to simulate the project when we have turbulent flow. So this is the domain, as you know, this is the domain of the flat plate. We have to check the thickness of the boundary layer for turbulent flow, but first let's check the conditions here. So we want to have turbulent flow. The plate length is still 20 meters, so we should increase the air velocity. This is the value that we chose, 3.6735. For the air velocity, the temperature is the same, 300 kelvins, but the plate temperature has increased 500 kelvins. And although we have heat transfer, the properties of the working fluid, which is air, is constant. The properties are constant. They are not affected by the temperature. They are usual values, but I always increase the viscosity a bit to have a good and good value for that. So let's go to the Excel file first. We have density or rho. Let's call it density this time. Viscosity, the length of the plate, the velocity of the air, and the Reynolds number. So density, viscosity, length, and velocity. How much was 3.735. So let's calculate the Reynolds number first. Density times length times velocity divided by viscosity. It's 5 million. And if you remember, we checked it. If the Reynolds number is more than 3 million, so we have turbulent flow. I know at the beginning of the plate, we will have laminar region, we will have transitional region, but what can we do? We, in external flow, there is we can use some turbulators to increase the to make the laminar or transitional length shorter, so to speed up the transition from laminar to turbulent, but we always have the laminar region and the transitional region. So we neglect that and we consider that we have turbulent flow over the plate to simulate the project. So for turbulent flow, delta is calculated using this formula. So let's calculate the thickness of the boundary layer so that we can be sure about these 4 meters for the height of the domain. 0.37 times x divided by Reynolds number to the power of 1 over 5. So delta times length divided by Reynolds number to the power 1 over 5 is 0.2. It's 34 uh, centimeters, so it's fine. It's fine for us. I mean the height of the domain, which is 4 meters, it's fine. We don't need to change it and modify it. So for those who haven't watched the previous video, I should start with a new fluid flow. The others can skip this, but now I want to use SpaceClaim instead of Design Modeler. So if you like to see the difference between this Design Modeler and the SpaceClaim, you can still watch these few minutes. And after that, we will continue in ANSYS meshing to generate a structured mesh. But so uh, you should always work in XY plane. This is the rectangle. You should add 2 dimensions. Oh, this is millimeter. So let me modify it to meters. So this should be 4 meters. And this should be 20 meters. Now the domain is correct. So this is the flow field. This is the domain, and we need. Okay, let's name the boundaries in ANSYS meshing. But before that, before generating the mesh, we have to think about the turbulence model that we are gonna use. I want to use k-omega-SST model because I wanna solve the boundary layer. So in these conditions, and since we have heat exchange, uh, we have heat transfer between the plate and the flow, and I'm going to calculate the Nusselt number in the next video. And for example, Nusselt number is an important and a crucial parameter in this project. So it's better to solve the boundary layer and have the y plus. So you should keep the y plus below 1 or below 5. Below 5 is fine, but if you can use finer mesh, please keep it below 1. To do that, you need two Excel files. I have provided these for you. The first one is y plus calculator. So it calculates the first layer thickness uh, with respect to your desired y plus. So for example, the Reynolds number is 5 million in this project. The length, the characteristic length is 20, and I want y plus 1. So it says that the first layer of the mesh should have the thickness of 0.1 millimeter. And then you should open the other Excel file, bias factor, and play with these values to get 0.1 millimeter for this one, the length or height of the first element. So, but what are these? L is the length of the edge, not the length of the plate. This edge, we should have a bias value, a bias, division to get y plus 1 over this edge, the plate. So this is the edge with the height of 4 meters. So L is 4. And now we should decide how many, divisions we want. For example, 1000. And now with the bias factor of 200, we get 0.1. I think it's fine, but we can increase it to 500. Oh no, it's too much. So 400, or maybe we can decrease the. Oh, sorry. This is the bias factor and this is the number. So the number, for example, if the number is 50, the bias factor is 1000. So we have to increase it to 20, I think. Yeah, it's fine. 250, 0.1 millimeter. The bias factor is 1000 and the edge length is 4 meters. So number of division is 250. Bias factor is 1000. 250 and 1000. This one should be reversed. Okay. Here, let's have 200s. We need this one, phase meshing. And this is inlet, just like the previous one. This is the plate, the outlet, and since this boundary is far enough, we call it symmetry. And now we can update the mesh. How many elements? How many cells? 50,000. It's fine. We can close it. Go to setup. This one, always check it. The double precision. It increases the accuracy of your simulation and the results. So it's a steady state simulation, 2D planar, pressure based. We need energy equation. The turbulence model is fine, k-omega-SST. And air, the fluid is air with these properties. And the boundary conditions, I should do it again. 6 point or 3 point, excuse me, 3.67. And the temperature is 300. The temperature of the plate should be 500 kelvins. Reference values, inlet, viscosity, temperature, always check these, velocity and density. And since we are going to export CF, skin friction factor, only density and velocity are important. So these are fine. Let's increase the accuracy by decreasing the residuals. initializing the flow now, and then run the simulation for 1000 iterations, for example. It's good, it's not bad. They're decreasing. The trend is important. So let's decrease it a bit more. It's fine, I believe, but we will wait. It's done. Now the simulation is converged. This time let's first have a look at the flow, the velocity field. Wow, this is the velocity field. The temperature, see here. It's good. And now let's export the skin friction factor. So for those who are new to this channel, we can use XY plot to export skin friction factor. Since the plate is horizontal, the plot direction is in X direction. And you can find skin friction factor, skin friction coefficient under the wall fluxes. Here you can see that skin friction coefficient. You can see surface Nusselt number or total surface heat flux, but you should watch the next video, which is about Nusselt number. As I mentioned, in most of the time, you have to use a manual method, a manual way to calculate your Nusselt number. It's really important to report the correct value in your papers, in your, I don't know, reports, conferences, because people try to do your work for their validation, for validating their results. And if you use a wrong method, they can't validate your work. So here, skin friction coefficient on the plate. This is the plot that you can see. This is the skin friction coefficient, and as I mentioned, you can export it. You can select this, check this, order points, and C, so CF turbulent flow.y. So if you go there in FFF1 fluent, here you can see that. You can copy and paste it. Oh, this is empty. You can paste it here. Let me copy these two and delete these. So this is CF from Fluent, the Reynolds number. Oops, this one. Because at the beginning, it's not correct. So this is the Reynolds number. But I need to change the velocity to 3.6735. Now, at the end of the plate, we have 5 million for the Reynolds number. And the formula in turbulent flow, as you can see, these formulas are different from what we have in laminar flow. So pay attention to that. 0.0592 So 0.0592 divided by Reynolds number to the power 1 over 5, which is 0.2. And now we can compare these values. So let me draw them. So this is CF from Fluent. I need to add this one. And as you can see, in the fully turbulent region, which is somewhere here, we are pretty close to the formula we have. But here, at the beginning, sections and locations, we have a bit difference. This is because we calculated the CF, the skin friction factor, using this formula, which is valid in turbulent flow region. But as I mentioned, we always have a laminar region and a transitional region. So that's why you can see this difference here up to, for example, 5 meters. After that, we're okay. It's okay. It's not a huge difference. But at the beginning, since the flow is laminar and we calculate it based on the equation which is valid in turbulence flow, so we have a bit error. And what else? I think it's let's see velocity vectors to see the boundary layer. See, we have more cells because in turbulent flow we have to have more cells and finer cells to capture the boundary layer. As you know, the boundary layer is really close to the surface in turbulent flow, and this can be seen in these figures. If you compare these vectors with the vectors we had in the previous video, which was in laminar flow, you can see the difference of the boundary layer in laminar and turbulent flow. So I think that's enough for this session. In the next session, we will calculate the Nosov number. That session is really special. Don't uh, don't miss it because it's huge and it will be helpful for you. So once again, thank you for watching this video. Please subscribe to the channel, give us a thumbs up. And if you find these videos useful, please share them with your friends. Please comment. And that's it. Thank you. Take care of yourself and have a good day, night, or time. Goodbye.